inside the giant aircraft manufacturing empire. 1. Introduction and Grand Overview. In an era where artificial intelligence and industrial robotics have become the foundation of every manufacturing discipline, a new generation of factories has emerged. No footsteps echo across the production floor. No manual rhythms shape the pace of creation. Instead, precision, harmony, autonomous orchestration. Welcome to the fully automated commercial aircraft manufacturing center, a symbol of the future where every centimeter of metal and every layer of advanced composite is shaped with flawless accuracy. Here, machines do not simply perform tasks, they execute decisions. They optimize themselves. They collaborate. Let us embark on a journey, step by step, through design, material science, structural assembly, interior creation, testing, and the final moment when a new aircraft touches the sky for the very first time. 2. Digital design and simulation. Every great machine begins with an idea, but here, that idea manifests as pure light. Gigantic holographic 3D models float in mid-air, generated by multi-dimensional simulation engines. Billions of aerodynamic calculations are performed in seconds. Artificial intelligence continuously reshapes each curve of the fuselage, each wing surface, each load-bearing frame, optimizing for lift, drag, fuel efficiency, structural integrity, and long-term fatigue performance. No physical prototypes are required. Everything unfolds inside the digital twin, a complete virtual replica of the aircraft in every operational state. Hot weather climb, turbulence, extreme crosswind landing, lightning strike, rapid decompression, and beyond. Here, design is not simply created. It evolves, it adapts, it perfects itself. 3. Advanced materials and composite fabrication. With the digital blueprint perfected, the journey of matter begins. Inside sterile, climate-controlled cleanrooms, AI-directed robotic arms lay down ultra-fine composite fibers with microscopic precision. Layer by layer, the structure grows. Stronger than steel, lighter than aluminum, and engineered for decades of flight. Composite sheets are pressed, heated, and cured inside high-temperature chambers. Every variable, humidity, compression force, thermal gradient, is regulated and analyzed in real time by autonomous systems. Wing skins, fuselage sections, floor panels, and control surfaces emerge from these chambers not as handmade parts, but as algorithm-crafted components. This is material science elevated to its highest form. 4. Metal form and airframing structure. Metal fabrication has moved beyond the boundaries of traditional engineering into an era where precision is measured not in millimeters, but in microns. This is where raw alloys are absolutely controlled. Inside the metal chamber of the automated forging facility, huge aerospace-grade ingots of aluminum, lithium, and titanium are transported by magnetic levitation rails. Each block is scanned, mapped, and entered into the factory's quantum-optimized workflow system. Every molecule of the material is calculated. Once the ingots reach their locations, the CNC supercells, powering machines that move as gracefully as surgical instruments, go to work. The cutters rotate at ultrasonic frequencies, carving through the metal with such precision that surface finishing is almost unnecessary. Each cut of the cutter head is calculated in real time. Temperature, stress, vibration, power consumption, all are constantly analyzed and adjusted. Nearby, plasma arcs are ignited, sending blue, white sheets of energy cutting through reinforced alloy composites. The cuts are so clean, so tightly controlled, that the material barely experiences any thermal deformation. Here, the plasma doesn't burn the metal, it shapes it. Next, the components are transferred to synchronized arrays of robotic arms, dozens of arms moving in harmonious rhythm. They weld using intelligent arc guiding systems, creating seams that are not only strong, but also structurally delicate. Other arms drill routing slots, apply structural adhesives, or install high-strength fasteners with sub-millisecond response times. Every movement is part of a choreography perfected by trillions of simulation cycles. Above, a flock of automated inspection drones dances on the frame aircraft in development. Each drone carries a multispectral laser scanner, capable of detecting defects invisible to the naked eye. Tiny cracks, density variations, geometrical deviations at the nanoscale. The system compares every scan point to a digital twin of the aircraft, an evolving model that is constantly updated from thousands of sensors embedded throughout the factory. If even a single contour exceeds the tolerance limit, tens of microns, thinner than a human hair, the entire production line grinds to a halt. Instant diagnostics, root cause tracing, structural analysis, predictive corrections. In seconds, adjustments are sent across the line and work resumes with new precision. The airframe begins to emerge, slowly at first, then clearly visible. Bulkheads, struts, ribs, longitudinals, each part connects with mechanical perfection science, creating the skeletal strength that supports near-sonic flight. The structure is both rigid and flexible, designed to withstand the turbulence, extreme temperatures, and relentless pressures of tens of thousands of flight hours. Here, metal is more than just a material. It is a memory. It remembers every force. 5. Mass modular assembly. Wings, fuel, tail. This is the moment when the individual parts become a unified machine, where thousands of individual components begin to transform into an ocean-going aircraft. In the heart of the hangar, Titan-sized robotic cranes glide effortlessly on tracks above. Their arms reach out with the calm precision of mechanical giants, gripping wing assemblies longer than a city bus, each made of carbon composite layers, fuel cells, control actuators, and lightning protection nets. Every movement is stabilized by gyroscopic AI algorithms that counteract even the slightest vibrations. Each segment moves on magnetic levitating platforms, floating gently like monoliths guided by invisible streamers electric. Meanwhile, the vertical tail and horizontal stabilizer, newly machined and structurally validated, are ready for integration. As these massive components approach the central assembly, the environment changes. The modules begin to slowly converge. Microthrusters on the flying platforms make microscopic adjustments, a millimeter to the left, half a millimeter down, a fraction to the right. Then, the magnetic docking clips are assembled. The wings fit neatly into their root joints. The tail structure fits into the tail frame in one seamless motion. Instantly, thousands of robotically assembled parts are deployed. Some tighten high-strength bolts with intelligent torque control systems. Others perform friction stir welding, creating joints stronger than metal. A swarm of microrobots moves into the internal compartments, bonding the layers structure, industrial adhesives, and internal inspection of every connection. Every assembly is validated. Every joint is scanned. Every tolerance is checked against a digital replica. Slowly, frame by frame, connection by connection, the full silhouette of the aircraft emerges. The fuselage is perfectly cylindrical, the tail shaped for stability and elegance. What was once a collection of independent parts is now unmistakably an aircraft. Aerodynamic, symmetrical, majestic. A form born of physics, perfected by automation, destined for the skies.
6. Electrical and electronics integration. Inside the hollow fuselage, which had been silent and aluminum just minutes before, a living network began to form. From both ends of the aircraft, specialized cable-laying robots glided into place. Their articulated arms reached out with pinpoint precision, guiding hundreds of kilometers of wire into place. Each bundle of wires was categorized by function: power, data, navigation, communications, and routed through specialized conduits built into the airframe. The robots pulled, threaded, and anchored each wire with perfect precision. Not a single cable was twisted. Not a single connector was out of place. Each joint was tagged with a nano-printed identification tag, instantly recorded in the digital copy of the aircraft. Their multi-spectral cameras analyzes each connector using optical and thermal signals, confirming continuity, resistance, and shield integrity in real time. Behind the wiring corridor is the avionics engine, the technological heart of the aircraft. The cooling systems begin to operate smoothly and steadily. The systems start up in perfect sequence. Environmental control system, sensor array.
7. Cabin installation and interior assembly. An aircraft is more than a machine. It is a space designed for human experience. Robotic arms slide each interior panel into position with perfect alignment. Windows are mounted with micro-level pressure control. Overhead bins are installed by 6-axis balancing robots. Seat rows descend into the cabin with flawless precision. Lighting systems are programmed with soft gradients, engineered for comfort, circadian support, and energy efficiency. Piece by piece, a comfortable and elegant environment takes shape within the metal frame. 8. Painting and exterior finishing. Outside, the aircraft receives its identity. Surface analyzing robots examine the metal skin for imperfections invisible to the human eye. In fully sealed paint chambers, robotic sprayers apply layers of coating with uniform thickness measured in microns. Airline liveries, graphic patterns, and logos are projected through laser-guided templates and rendered with mathematical precision. When the final coat settles, the aircraft emerges with flawless, seamless exterior, a polished symbol of engineering purity. 9. Ground testing and system validation. Every system must prove its integrity. Sensors and robotic diagnostic units interface with the aircraft's electronic architecture, pulling live data through thousands of channels. Flight controls, braking systems, electrical redundancies, hydraulic pressures, and structural responses undergo exhaustive automated verification. The aircraft is towed across specialized testing lanes and subjected to simulated weather conditions, vibration cycles, and environmental extremes. Only when every metric meets the highest standard does the aircraft earn permission to take the next step. 10. First flight, delivery, showcase. And then, the moment every machine in the factory has worked toward. The hangar doors slide open. Sunlight washes over the newly completed aircraft. Its polished skin glows. The aircraft rolls toward the runway, monitored by drones and remote AI systems. Engines start. Navigation lights flicker to life. Acceleration builds. Smooth, powerful, confident. And then, it leaves the ground. A perfect test flight marks the end of one journey and the beginning of countless others. When it returns, the aircraft is guided to the delivery bay, prepared for handover, and presented as a masterpiece born from intelligence, automation, and human ingenuity. This is not merely a production process. This is the future of aviation, a future where creativity and automation rise together.